how about we review for the midterm? Do bring a calculator. Specifically, there will be some problems involving utility theory. In fact, there's only one, but I made it into a 3-part question. So you'll have to do a little math to answer it, and then you'll answer another question about it. And truthfully, you won't really need a calculator if you're one of those kinds that can do arithmetic in the margins really quickly, but it wouldn't hurt. It'll help you feel more comfortable if you have a calculator maybe, right? If arithmetic slows you down and there's a limited time to take the test. So I recommend you all bring a calculator. Here's what the test will be about. We covered utility theory and breadth first search and uniform cost search and A-star search and genetic algorithms, and we briefly talked about a few other optimization techniques. So that's what'll be on it. And by the way, we briefly talked about that, so this is like maybe one question. This will be most of them, yes. We did not actually do a programming project involving other optimization techniques, right? I just basically, during one lecture in class, mentioned them, and I did expect you to kind of hear it and get it a little bit. But no, I will not be asking you for pseudocode or details of the algorithm or how it works or anything. If you just knew kind of how hill climbing works, that should be good enough. Simulated annealing is basically hill climbing with perturbations, and the perturbations cool down over time. Particle swarm optimization was inspired by birds, and they flock around and they gravitate towards the center point and the best point they've ever seen. If that's all you remember, you're ready for this test. And ant colony optimization was inspired by ants who leave pheromone droppings on the ground, and they follow the path, and that tends to optimize the path over time because pheromone evaporates and ants make mistakes when following the pheromone trail. And the more ants that follow it, the more reinforced the trail becomes. And that's one thing you can do in simulation to make a optimized path. Interestingly, ant colony optimization really isn't very different from using a genetic algorithm to evolve a genome that represents a path. And then every time you mutate it, you're kind of just tweaking the path, right? And when the path gets better, you keep it, and when it gets worse, you throw it out. You see how ant colony optimization and genetic algorithms are almost the same thing. It's just that one is inspired by ants and the other is inspired by evolution. Okay. So, in fact, I think that's all I have to say about this one, so we can knock that one off of the list. Any other questions on these additional optimization techniques? Anybody not remember one of them and want me to repeat it really fast? Yeah, sure. Hill climbing is kind of like a genetic algorithm with only one member of the population. You just have this one vector and you mutate it. And by mutate, I really mean you try all of the adjacent points, or you perform all of the possible actions. You do whatever you can to produce all of the next states you can be in. Then you evaluate all of those states and see which one's the best, and you throw out the others and repeat. So you just keep perturbing the best spot until it reaches an optimum. One thing you should know is that hill climbing is susceptible to local optima, and you should know what that means. Whereas genetic algorithms are one of the few optimization techniques we know of that is really, really good at avoiding local optima. So if you want a global optimization algorithm, genetic algorithms are key. If you want a local optimization algorithm, hill climbers are good. Hill climbers are faster. Genetic algorithms they find the global optimum rather than a local optimum. And that's kind of what this is about. And particle swarm optimization is also a global optimization technique. And this is more of a path-finding method. And this is also a global optimization technique. Yes? Hill climbing, when I say one, I mean it's only one member of the population, not one population. And yes, hill climbing takes far fewer steps than a genetic algorithm, because a genetic algorithm wastes its time moving lots of random members of the population in random directions, whereas a hill climber is basically just going straight for the goal, right? Hill climbing is a greedy optimization technique. Greedy optimization techniques they have that problem of local optima. If there's a wall, they run straight into the wall and then say, what do I do? Whereas particle swarm sends out the birds, and the birds flock all around, and some of them fly around the wall, and some of them find the goal, and then they all follow and get to the goal, and it basically finds the global optimum. One thing I want to say here is, it is my personal opinion that a good test is not about trying to trick the students, but I do have to ask questions that I consider on the boundaries of, between those that get it and those that don't get it. Because I am trying to discern between, some of the questions will separate the B from the C students and some separate the A from the B students. So some questions will be a little bit out there, but they shouldn't be things I didn't teach. I'm not going to ask, did you read my book? And on page 214 in paragraph 3, there was this one little sentence where I made a statement, and if you didn't remember that, I'm going to get you, because I don't care about that. I just care if, did you get your assignments done, and did you understand what you did? My attitude is, if you turned in working code, that implies you understood that algorithm really well. I mean, you could produce pseudocode on demand. You know why we did stuff. You get it. Okay, so anything that you coded up, I feel totally comfortable asking you hardcore questions about it because you turned in working code. Surely you didn't just get it working magically, right? I think you should understand your code. So my questions are designed to target that situation. Did you understand your code? And if you did, hopefully there's no studying you can do. You understood your project, so you're ready for my test, is what I'd like it to be. But of course, studying does tend to help, so I kind of recommend you do study a little. If there are questions about pseudocode, they will expect very high-level stuff, because it gets really hard to discern between the students that wrote high-level pseudocode but understood it and the students that just wrote high-level pseudocode because they don't know how to code. And this isn't a programming class anyway. This is a do you understand basic AI algorithms class. So if I ask for pseudocode for, say, breadth first search, here's about what I would be wanting. Q equals make a queue, push first, hey, I just made an underscore, it didn't appear. There it is. Push start, wait, how about q dot push start state? Something like that. And then while q not empty. And I'm actually putting a lot of symbols here. If you didn't have those symbols, if you just wrote it in words, just as good. I'm only doing symbols because I've been coding for so long that those symbols have meaning to me. And then if you just said pump the queue, that would probably be too high level. At this point, I'd say to myself, wait a minute, do you get it? But if you said something like C equals Q dot pop or DQ or get something out of the queue or retrieve the next item or anything that indicates you get what we're doing, and Q dot push each of C dot neighbors. See how that's bad? That's not even code. That wouldn't work. But the concept is you're going to visit all of the neighbors. I guess what we really should say is for each neighbor n of C, q dot push n. Okay, and now we've just about did it. However, what's missing? There's a few key concepts. One is we don't want to revisit the same states. Now, if you were searching a tree, maybe it wouldn't matter. But if you were searching a grid, it definitely would matter. The point of not revisiting states is to kind of turn it into a tree, right? So you should be aware of details like that. It's not always necessary to have a set of states that you visited in breadth first search. It's necessary when you're searching a graph that's not already a tree. If all of the children are down on the tree, then just searching the tree does its job. Did you follow that? Okay, so not all implementations of breadth first search have that queue, but we did, and you should know that maybe you need one. So s equals set. And you might add in here, if C is not in S, s.add C, or, well, we know it's not. That should actually be here, like that. There you go, something like that. Okay, there, now we've done breadth first search. Except we didn't detect the goal. Somewhere you better say there, how about here? If C is goal, then do a dance. You should certainly understand how to get from the goal back to the start state. How do you do that? Yeah, you should have been keeping track of how you get from each C to corresponding N. Oops, that should have been N. Oh, I made a bug in my pseudocode. I would have taken off a, oops, you made a mistake point for that. But notice, just because you know how to get back from the goal to the start doesn't mean you have to express it, because unless I asked for it. If I did ask for it, you should know how to do that. But, okay, this actually turned out a lot more formal than I intended. I was trying to show you how informal I expected, and I don't know how to write informal stuff anymore. But very high level is all I'm going for. As high level as you can be while still expressing that you kind of get it. Did that answer the question?
You can't just say you search breadthly first.
The algorithm is 1, go to Wikipedia. 2, search for the algorithm. 3, paste it in your code. 4, get it working. Truthfully, that's a great algorithm. It works most of the time. And as a student, you should know that one. But that is an important algorithm.
4, make sure it doesn't look plagiarized.
Yeah, 4 changes so it doesn't look plagiarized. Rename the variables and add white space.
Change where you declare each variable.
Okay, so you should know how to implement these algorithms. We've talked about them enough. I kind of think there's not much more to say about them today. Any questions? Yeah. Okay, the question is, do you need the reparenting step in uniform cost search or only in A-star search? The answer is it's more important in A-star search because the situation comes up more frequently. It does also come up in A-star search, or excuse me, it also comes up in uniform cost search. And here's basically the canonical example. And if I ask you a test question, it'll probably be related. Okay, what's the shortest path to this goal? By the way, the start state is the top, the goal state is the bottom. Obviously, the optimal path is to follow the left branch, right? Okay, if you do uniform cost search, which way will it find the goal first? The right branch. The reason it will find the right branch first is because 2 is smaller than 3. And even following uniform cost search, this one comes out first. But you're not really done until the frontier has moved on, until nothing in the queue can lead to the goal. And so you do have to have a step where you can reparent. However, that issue only comes up for the width of the frontier, which is always 1. Does that make sense? Meaning, however long it takes to cycle around everything on the frontier is how much pumping you do of the queue until this issue is not a problem with uniform cost search. With A-star search, it's possible, because the frontier is not uniform, that quite some time later you will arrive at a better path to some state. Therefore, with A-star search, you can end up with drastically different paths, whereas with uniform cost search, you can only end up with up to 1 step was inefficient paths. That didn't come out in very good English, but I think the concept was there. Do you kind of get it? Technically, this is necessary in the code. In the assignment, if you actually omitted this step entirely, it actually still worked in most cases, and no one could even tell the difference in the visualization of the algorithm. So, yeah, it's not the world's most critical issue. It's just something that's necessary for technical optimality. And if you didn't care about optimality, why are you using uniform cost search, right? A genetic algorithm or something else will be so much faster because it doesn't search the whole space. Therefore, you probably do care about optimality if you're using uniform cost search. Therefore, you probably do want to take the time to add this 1 extra step to your code because you can and you want to be optimal. All right? And you should know how to do this. I mean, it's just a matter of, hey, this state already exists somewhere because it's already in my set of states I visited. So just look that up and then say, hey, your parent is not this one. Your parent is actually now this one. And if you can do that, then you get it. Okay? Know how they differ. You should know what a heuristic is. Do you know what a heuristic is? Should I repeat that?
Best guess.
It's just something that helps improve the algorithm. There's one rule with the heuristic in A star. What is it? Yeah, don't overestimate. Just underestimate it. And is the heuristic added to the cost or subtracted, or is it sorted by the heuristic? What does the heuristic do?
Sorted by it. It's sorted by it, added to.
Yeah, you sort by the cost plus the remaining heuristic. And that improves it because at the last moment, the last step when you're about to hit the goal, as long as you're underestimating the remaining distance to the goal, it's going to be 0 at that moment, right? And so at that moment, it will be optimal if the next thing that comes out of the queue gets you to the goal. And that addition of adding the remaining cost biases it away from searching the states that get really, really far away from the goal. So it's a good heuristic. You don't always have a heuristic, so uniform cost search is kind of more general. But if you do, A star search is faster, and you should know that. If you overestimate, it tends to approximate greedy search under certain conditions. It basically definitely ends up suboptimal, and what it does, I guess, depends on the details.
So
You just have to think about how
sort of thing.
it really screws up the algorithm pretty badly if you overestimate the heuristic.
The frontier is like the.
But it can screw up the algorithm really badly. Sometimes it doesn't. Sometimes it works. Yeah, A star basically makes the frontier lean. Have you seen While You Were Sleeping? He's leaning. Oh, okay. It was a movie. I said leaning. It makes the frontier lean towards the goal.